Okay, so we've been talking about intermolecular bonds, and we've been generally talking about intermolecular bonds as they hold pure substances together, like water holding water molecules and that sort of thing. We're switching gears now and going to talk about mixtures. What sort of intermolecular bonds do they have going on? So with regard to mixtures, one of the terms we've talked about before is you can have a homogeneous mixture or a heterogeneous mixture. If a mixture is homogeneous mixture, we call it a solution. A solution and homogeneous mixture can be used interchangeably. Now, when you think of solution, you usually think liquid. It doesn't have to be liquid, okay? But we're going to talk about liquid solutions and intermolecular bonds as the solute and the solvent mix. So terms that actually we already covered in Chem 1 look like this. So when you work these problems, you're probably going to draw pictures. Remember that if it is a liquid that you're adding it to, the thing that's in the greater amount is the solvent. Okay, and the thing that's added in lesser amount, it could be a solid or another liquid or even a gas, is the solute. And if your solvent is water, then we call it an aqueous solution. Remember, the abbreviation for aqueous is AQ. Okay, so that's kind of what we have going on. Again, what we're skipping to. Did you have a question? Or? Oh, you just...
Sorry, I heard them talking and it caught my ear.
So yeah, we're starting on part 6. So we're going to actually then have to kind of pick apart what's happening in this mixture with regard to intermolecular bonds. It's exciting. We have two things that have to join together. It's wonderful. So examples of solutions. Now I was talking to my husband about this. I'm like, would you call it that? And he's like, no, not really, but that's okay. For instance, a solution is just a homogeneous mixture. As I'm walking around this room right now, most of it's nitrogen, some of it's oxygen, so it's about an 80-20 mixture. It's pretty uniform, so we call that homogeneous mixture. In this case, the thing that is in major amount would be the nitrogen, in minor amount would be the oxygen. So nitrogen would be the solvent, and O2 oxygen would be the solute. I buy that, I suppose. When you buy a can of pop, they don't call it sugar water for nothing. But if we just kind of focus not on the sugar, but if we focus on what makes it fizzy, which is the carbon dioxide, that would be the solute. And the thing that's in most amount, the solvent, water. Hydrogen and palladium. Basically, you infuse solid palladium with hydrogen. So hydrogen, again, the solute. This is the one I asked my husband. I'm like, are you serious? But I guess it kind of makes sense. When we buy rubbing alcohol, it's an impure amount of isopropyl alcohol, rubbing alcohol. So in that case, most of it is this isopropyl alcohol, but it's not entirely pure. So we have an amount of solute that is in there, and in that case, the impurity in this case is H2O. That's the one I was like, no, that's not, but it's true. Salt water goes back to an aqueous solution of salt water. You have as your basis, your solvent is water. You've sprinkled it with solid sodium chloride. Okay. Now this actually is an example of a solid solution. When you get your metal alloys, basically at the factory they mix them up so they're homogeneous, but you don't have any chemical bonds between those different metals that were made to make your alloy, that went in to make your alloy. So in case of brass, you have a bunch of copper and it's sprinkled with zinc. So copper is your solvent and zinc is your solute. It's frozen, okay, in order for you to use it as a piece of brass. So I've got some pictures to kind of show you the whole mixture process. So we can kind of think of it stepwise, kind of like you think of, it's to be a kind of a Hess's Law problem where you put together the baby steps to make your overall thing that happens. So in order for a solute which is a minor amount, to mix with a solvent, basically the particles have to split apart. So here we have the solute particles splitting apart. We have the solvent particles splitting apart. So I'm going to, let's see how do I say this, to remind you of when you break bonds, energy is required. When bonds are formed, energy is released. So I'm going to tell you that this actually takes energy for these two things to happen. Breaking those bonds, and then it's kind of fun, once they're broken apart, they're reassembled, and ta-da, our solution, or our homogeneous mixture. So think of it this way. We break the bonds up here, requires energy. When bonds are formed, energy is released. So we're actually going to kind of come back to that. So these new bonds that are formed are different than it was in the pure substance. We're actually today going to go back to the whole 7 or 8 different types of intermolecular bonds. So the intermolecular bonds that form as a mixture aren't necessarily the same as forms they were in their pure state. So yeah, here's our list. Okay, this is one I have printed out, put on my refrigerator in my office. Strongest is ion-ion, then we go ion-dipole, then we go the special situation of dipole-dipole, hydrogen bonding, where you have a hydrogen-oxygen, a hydrogen-nitrogen, or a hydrogen-fluorine. I think that's right. Nope. Nitrogen, oxygen, nitrogen, oxygen, or fluorine bonded to a hydrogen. Then we go ordinary dipole-dipole, and then we go to a mixture. You can have dipole-induced dipole. I told you a while back that anytime you run into the term dipole, I was hoping that you'd remember polar. And induced dipole are nonpolar substances. So notice little asterisk says that this would be a mixture for sure, this would be a mixture for sure of something that is polar and something that is nonpolar. And then last but not least, we have induced dipole. Now, not to say that hydrogen bonding and ion-ion and induced dipole cannot exist in a mixture, because they totally can. But for instance, if you have two nonpolar substances, like if your solute is nonpolar and your solvent is nonpolar, when they go to bond in a mixture, then you have induced dipole going on. So note that ion-dipole and dipole-induced dipole, you're talking about two different substances that are coming together, so it has to be a mixture. And these guys could be mixtures or otherwise. An exception I have here is we talked about hydrated salts. And actually, all it is a salt is an ionic compound. We can take like copper 2 sulfate, an ionic compound. Some salts, just because of actually the electrons or their crystal nanostructure, actually pick up waters of hydration. In the case of copper 2 sulfate, a common one is pentahydrate, 5 waters of hydration. This is an example where actually within the pure substance, I hate to say this, but you actually have ion-ion intermolecular bonds, and then you do have ion-dipole. I'll call ion-dipole instead of hydrogen bonds. Okay, so ion-dipole means that you have something that's an ionic substance, and dipole, I'm hoping you guys think polar. Okay. So I'm going to show you some pictures. A good example of something that's polar, favorite solvent, and a large amount you can dissolve solutes, is water. So these little Mickey Mouse things, these red and white things, those are water molecules with the oxygen and the 2 hydrogens. We talked about why they're bent. The molecular shape is bent. So here we see a salt, potassium chloride. It almost looks like it's getting eaten away by those little water molecules, carrying off the positively charged potassium ions and carrying off the negatively charged chloride ions. But if you look closer, you can see what takes what. I mean, it's no mistake that this positively charged cation is being associated with the oxygens, which are partially negatively charged. Okay, they're partially negatively charged. If we pick on the chlorines up here, that chlorine's getting ganged up on. Why? By these partially positive hydrogens with water molecules in this film. And an aqueous solution of potassium chloride is formed. Makes sense. Similarly, we have, this doesn't say what ionic solid it is, but the big fat ones would be the negatively charged anions, the small white ones would be the positively charged cations, and then again you can kind of see them being whisked off. This would be your solid crystalline lattice right here being etched away by the water molecules. I'm trying to say something about UFOs. I've got UFO on my brain. This actually kind of, again, talks about the breaking bonds. So, we said a few minutes ago that you have to break the bond of your solvent, you have to break the bonds of your solutes, and then these would be the new intermolecular bonds that are formed. Again, I kind of stumbled. I'm like, okay, so I got the whole ion. In this case, we're going to call this ion dipole instead of ion hydrogen bond. It's ion dipole because water has a dipole. So be thinking about this. Energy required. Energy required. Okay. Sorry. And this one is energy released. Goodness. Dipole, induced dipole. Now, sometimes there's terms in science, if you think about it, you're like, oh, I think I know that, and you probably do. So dipole, think polar. Induced dipole, think non-polar. And we're talking about mixtures, so this would be where you have with regard to your solvent and solutes, something's polar and something's non-polar. Now, as it turns out, I'm going to introduce something that's called like dissolves like. And this works actually, but it's this whole polar non-polar is not as favored as if it's like things that are trying to dissolve to each other. So let's take a look at getting oxygen gas to dissolve in water, what that looks like. So actually, I visited this a few times. Well, maybe this is a different one. Bromine, which is Br2, is over here. And hopefully you would tell me that that is nonpolar, just like O2 is nonpolar, definitely nonpolar. Okay, and we have water here, and it's very similar to the video we saw a minute ago, where if we do successfully get a solution to form right here. Now, let's see, it's hard to, like, I get ahead of myself. So like dissolves like. I can't write. Oh my goodness. It is Monday. So water, hopefully you would say polar. Now, they actually don't want to dissolve in each other. But if this is still bromine, I love the red on the dark. If this is still Br2 liquid, okay, and this is H2O liquid. Oh goodness, that didn't work. But can you see where the discolor of the H2O says it's not pure H2O? So what this is actually telling you is just based upon the color, we know that actually we have a mixture up here. Some of our Br2 has actually snuck into, has snuck into the H2O. So up here we have a mixture. And again, if we were to look closely at those, the connections, the intermolecular bonds between that Br2 liquid that was successfully infused, I think of our fruit drinks infused, That Br2 liquid that was successfully infused into our water molecules, it's got to be induced dipole-dipole in molecular models. Let's see, acetone, and we'll be talking more, I think probably we'll get to it on Wednesday, about kind of different what we call functional groups. This is color-coded. The blacks are carbon, the blacks are carbons, the whites are hydrogens, and this red is an oxygen. And what it's showing is that this right here, the carbon oxygen, our oxygen is partially negative, and the rest, or the kind of underneath it, is partially positive. Carbon disulfide is right here. Carbon disulfide, CSS. Carbon disulfide is maybe not so surprising if you find carbon dioxide, CO2. Do you remember that's nonpolar? Carbon disulfide is also nonpolar. So just kind of substituting, instead of oxygens, we have sulfurs. So it's nonpolar, so the only way you're going to get carbon disulfide to go ahead and dissolve into or become a part of a mixture with acetone is, again, an induced dipole-dipole in a molecular bond. That's all it's saying. One of the things that we did before was to make the partially negative regions kind of bright red, the partially positive regions blue, okay, and this would be, can't see it much, but it's kind of a little pink there. So this would be a momentarily induced dipole. So where this should be blue. Whereas this looks red to me. That looks blue to me. So anyway, I hate to complain. Again, this is with a different author, but this should be blue because blue means electron deficient. But go ahead and say it up here. Partially positive, partially negative.
So the two electron not, that has to be electron, what did you just say, electron?
Deficient and electron rich go together.
Attract,
mm-hmm.
Because two positives aren't going to attract.
Right.
Okay, cool. Sorry.
So here's where I kind of get into rules of solubility. Like dissolves like. And I think of rules of solubility, I think that was terrible. Remember where in Chem 1 when we did the whole ionic compound and which ionic compound would be soluble, which would be insoluble? Actually, no, that's the thing you're going to do in Chem 2. That's a terrible thing coming up. I know, sorry, sometimes I forget. Anyway, like dissolves like. So in general, that means that polar substances will enjoy intermolecular bonding in a mixture with other polar substances. Okay? And it's more of an exclusion thing. If you were to try to take something nonpolar and dissolve it in something that's polar, it's kind of like the polar things are just enjoying each other's company so much that they basically exclude the nonpolar things. Good thing is, nonpolar substances generally would dissolve in other nonpolar substances. Okay, so you have polar-polar, dissolve, nonpolar, dissolve. Solubility, just in general. So, in general, put another way, polar substances will not dissolve in nonpolar substances. Okay. I have a video to kind of show you how that works. But we've already seen it just a little bit ago with taking carbon disulfide and dissolving it in acetone, or taking I2 or O2, dissolving it in water. Those are polar and nonpolar things. It can't happen. So water is a great abundant solvent. It's polar. So the problem is if you try to dissolve nonpolar things in there, it's not going to dissolve. If you have something that is nonpolar and you want to make a solution out of it, well then you better grab a nonpolar solvent. Now, if you have something that's kind of borderline, it is it's polar, but its polarity is not very strong. then it goes into the nonpolar campaign, the nonpolar bucket. All right, so here we go. This is kind of reminds me of Hess's law. This is what we talked about, kind of the opener about breaking the bonds and forming the bonds. So if we have two pure components, and this actually is along the y-axis, you have energy, okay, or energy in form of enthalpy. So we have to put energy in to separate the solvent molecules. We have to put energy in to separate the solute molecules, okay, or particles. They could be ionic compounds. And then as up here, we're at the top, we've added as much energy as required, and then as bonds are formed, energy is released. So that's kind of how this works. Okay. So we have a couple of different things that might occur. So for instance, these are different scenarios. We have the blue scenario, where if you compare the N energy here versus the energy of what you started with, notice that you have less energy, okay, than you ended with. So this is sucking in energy, it's endothermic. The enthalpy of the solution would be this. It would be positive, greater than 0. And so actually this is going to endothermic things rob energy from the surroundings. So this is a case where it's going to get cold. Literally, your solution will get cold. Let's compare it to this scenario, where if you compare the amount of energy required to break the bonds, okay, energy required versus energy released, in this case, you have a net release into the environment. You have a negative enthalpy of solution. And in this case, your thing is going to get hot. It's going to release energy into the environment. This makes a great cold pack. This makes a great hot pack. Alternatively, you kind of have that middle scenario where it's right here. It's the black one. It's a wash. So basically, the amount of energy required to break the intermolecular bonds of the solvent and the solute are equal to the amount of energy that was released as those new intermolecular bonds are formed. And there's a name for that. We're going to call it I think it's some sort of perfect solution coming up. In this case, the change in enthalpy of solution is equal to 0. And as you might imagine, that's common when actually you have similar types of bonds that are broken as are being formed. So it's perfect. I said perfect, that's the wrong word. It's an ideal solution. Ideal. Okay? Where the intermolecular bonds broken, that energy required is equal to the energy released when your bonds are formed. And it occurs when you have similar forces that are broken versus versus formed. Okay. We're going to talk about Raoult's law later. And so an ideal solution is one where there's no heat required or no heat evolved when you're dissolving your solid, not dissolving solid, I'm sorry, when you're connecting up your solute and your solvent, and it obeys what we say Raoult's law. So a non-ideal solution can either be endothermic or exothermic. And when this goes back to, hopefully you remember your Gen Chem 1 days, when you have enthalpies that are negative, less than 0, is that endothermic or exothermic? A 50-50 chance. It is exothermic when it's negative, right? So this is exothermic, energy is released. And this is endothermic, energy is taken in. Yep. So you would figure it would be exothermic if on the downside that actually the bonds that are being formed are more favorable than the bonds that were broken. And you figure it's going to be endothermic if the bonds that are broken were more favorable than the bonds that were formed. Okay. So this is acetone that we looked at a little bit ago. Remember where that oxygen is partially negative, and then we have this region, it's in general partially positive. You can kind of see it here, negative, positive. Now, carbon tetrachloride, oh sorry, that's not carbon tetrachloride. Ethylene, I think. This right here is also polar. So we have two polar substances, and this carbon is partially positive, okay, and so it's butting up against the partially negative oxygen associated with the acetone. So, are you good with this? Does this look like a dipole intermolecular bond? It is. Okay. So like dissolves like. Now, a couple of terms with regard to dissolving stuff. If two things are what we call immiscible, that means that they won't mix. So immiscible things like we're going to pick on oil here in a minute. If I were to take vegetable oil and add it to my water, they're not going to mix. Water and vegetable oil are immiscible. Well, if water is polar, then that vegetable oil must be nonpolar, and you're totally right. Okay. Liquids that don't mix or solutes and solvents that don't mix are generally called immiscible. Okay. Now, why would things be immiscible? Well, in the case of my water and floating vegetable oil, it's because those water particles love those special hydrogen bonds they form with fellow water molecules, and they kind of exclude the vegetable oil molecules. Okay, so forces of attraction between unlike molecules are weaker than between like molecules. So immiscible and miscible, they sound so similar, but they just the opposite of each other. So immiscible, layers, they don't mix. Miscible means they do mix. Okay, now these are very generic terms. They're not, there's no quantitativeness involved here. But just in general, if we say things are miscible, that means they do mix. Okay. So if they're mixing, then they must be happy to go ahead and break their old bonds and form new intermolecular bonds. So oftentimes that will happen when similar bonds are being broken as they are in their pure state as formed in their mixture state. Okay, so like dissolves like. Yeah, I'm all about making like little poems or little songs. I'm not sure I can make a whole song out of that, but we'll see. So, antifreeze. I hope it's miscible. Okay? That would be an issue if you added it to your radiator and they formed layers. We're going to take a look at kind of the chemical nature of antifreeze. Why? Well, if we talk about like dissolves like, antifreeze must be polar, right? If it dissolves in water. So here's a picture of kind of what antifreeze might look like. Of course, you recognize your Mickey Mouse water molecules. Okay. And antifreeze is usually a type of a diol, which, see the water molecule here. The grays are the carbon chain, and then this is my antifreeze molecule here. I have, diols have two hydroxyl groups, which is an oxygen-hydrogen, oxygen-hydrogen. And just like the oxygen-hydrogen of water, we have partially negative, partially positive. So definitely polar and definitely willing to even hydrogen bond. Yeah, there's the formula for antifreeze, ethylene glycol. Two polar substances, like dissolves like. They look immiscible to me, I think. So this is probably kind of like I was talking about the water and the vegetable oil. Yep. They are immiscible. So again, this is talking about water and oil. Let's see what we think of this video. The cool cats, like the water molecules are the cool cats, and they're just all like, you know, cool cats all just like huddle together. I guess I should say insecure people kind of just huddle together, okay? And it's not that they won't mix with the other group, which is the non-polar substances. It's just that they're so busy mixing with each other. Okay, so they kind of, in that sense, like this, I think it used the word exclude. The oil particles, molecules are excluded from those water molecules doing their hydrogen bond thing. Because we know that actually something that's polar like water can induce a dipole. It just chooses not to. Okay, so here we have water, and this gray and white thing right here is simply a hydrocarbon. This could be your oil. It's not vegetable oil in this case, it's oil from your car. But oils in general are just a hydrocarbon. Okay, and how long is the chain? I don't know. Pretty long. Okay, the longer the chain, the more it is to be a liquid at room temperature or even a solid. So, now, so oil is nonpolar and water is polar. A good type of, and I don't have it here, I think I'm going to pick on it later, okay? Carbon tetrachloride is a great solvent if you're if you want to dissolve something like oil that is nonpolar. CCl4 is nonpolar, it's a liquid, well, carcinogen, but, so I wouldn't use it in large amounts, okay, but carbon tetrachloride is great for dissolving oil. All right, polarizability is kind of like a repeat. I think we talked about that. Polarizability is just the chance that something can go ahead and have a something that's nonpolar can go ahead and have a partially positive, partially negative end. Okay, like we saw with the O2 molecule. But polarizability actually doesn't work on just nonpolar things like O2 or I2. Polarizability actually gets us those dispersion forces that all compounds have. It's kind of weak induced dipole, okay? Now, one of the things we talked about is that the larger the atom or the greater the mass of the molecule, it's more polarizable. But we also talked about branching, and the more branching it has, the more squished together it is, the less surface area it has. So it's not just molar mass, okay? So those induced dipole, remember I told you, I kind of whined about it, that there's in London dispersion forces, London forces, induced dipole, it's all the same thing, okay? So as your polarizability increases, then you can get more of those induced dipole. So here we go. Let's go ahead and make a mixture of, it doesn't say what it is, this could be O2, probably O2 with a double bond like that. Okay, so we're taking water and we're going to dissolve oxygen gas in it. Of course, this is nonpolar, this is polar. Well, what needs to happen is that we need to have a kind of distortion of the field of electrons around the O2 molecule, so that actually near the partially negative side of the water, that will give an electron deficient part, partially positive for the O2 molecule, and ... there's your intermolecular bond. So that's how we get O2 dissolved in water, which, by the way, is important if you're going to go fishing. So those cute little fishes have their oxygen dissolved in water. We're going to talk about when it comes time for oxygen to be dissolved in water, actually there's a temperature aspect to it. And as it turns out, the colder the water, the more oxygen you can have dissolved in it. Okay, speaking of, I guess I got a little ahead of myself maybe now. This is all using water as the solvent. And in this case, these are all gases, and we're going to dissolve helium into water, we're going to dissolve nitrogen, we're going to dissolve carbon monoxide gas, oxygen, that's nitrogen, oxygen gas, and methane gas. How soluble are those gases in water? Well, right off the bat, without looking at the temperature, you can see that helium has the lowest solubility, okay, and methane has the highest solubility. These are all, by the way, gases are nonpolar. So the methane actually is got the highest molecular weight. It's most polarizable, and so its solubility is the greatest. But with all of these, it's just like I said a minute ago. Maybe when the waters get warm to go fishing, maybe those little fishies are oxygen deficient, because as temperatures increase, the solubilities of gases decrease. You can kind of see that with all of these. So solubility of gases. Here's some numbers to kind of go along with that graph. We have nitrogen, we have hydrogen, nitrogen, oxygen gas listed in order of increasing molar masses. Of course, oxygen is more polarizable than the nitrogen, so it actually has a higher solubility. Some things in science you're like, oh, well, that makes sense. And that's kind of the chemistry behind why the oxygen will dissolve more in water, because it's more polarizable. So, last couple of slides. I blew through this material, but a lot of pictures. So actually we have three substances here. We have carbon tetrachloride. Remember I said the CCl4, although it's a carcinogen, would make a great alternative to water if you're trying to dissolve something, because CCl4 is nonpolar. And then we have, up here, we have water, but also what's making that water kind of a brown color is the presence of I2. So, of course, I2 is nonpolar, water is polar, and so this is this dipole, induced dipole. Okay, dipole, induced dipole, making that mixture. Now I'm going to shake it up, and then what you're going to see is that those I2 particles, molecules, would rather be with the other nonpolar substances. So here we go. Without further ado, shake it up, give a little bit of time. And again, you have your water at the top, but now your water's clear. And the only reason it's clear is because that I2 has migrated out. Why? Because the I2 wanted to be with its nonpolar buddy. Okay. Now you also notice that the I2 changed colors from brown to purple. And I think that has to do with the frequency at which it's vibrating. So that's more of a molecular thing. I mean, at the molecular scale. Okay, so this actually is going to show you that same thing. These are nonpolar. I'll just put NP, and this is polar. So that's kind of what you saw. Now, one of the skills that you guys have been working on is to identify things that are nonpolar, polar, and nonpolar. So I'm hoping that's going to stick, because you're going to want to be able to do it on a test. All right, so we're done with part 6. So I'm not sure. Come and be surprised Wednesday if we'll go to part 7 or go back and pick up part 5. I'm thinking part 7.
I was being
Come and be amazed.